Yes, hello, is this audible?
Yes, teacher. Assalamu alaikum.
Walaikum salam. All right. Now, see, we had completed with the first chapter, electric field and charges. We'll begin today with electric potential and capacitance. But before that, see, in electric potential and capacitance, a lot portion of your calculus will be used. So we'll just do a quick revision of calculus and then we'll begin with the chapter. So, see, in your calculus, the portion which is required is your differentiation, and the other one is your integration. So first, let us discuss differentiation. Now see, this differentiation, it is a change-dependent variable. This is a change-dependent variable. Let me write it down. Change-dependent variable. Change-dependent variable. See, if you have dy over dx, this means that you are differentiating y with respect to x. If you have such a case, dy over dx. Now see, if you have a polynomial function, in case of polynomial function, you have y is equal to x to the power n. When you have y is equal to x to the power n, see how you differentiate. You usually differentiate dy over dx is equal to, see, whatever is the common, take it out first. When you have to differentiate it in this manner, means whatever is the common, you take it out. So you are differentiating x to the power n. N is the power, means the exponential power of it. So that's the constant and it comes out. And what happens to what is left? You subtract 1 from it. Like if you have x to the power 2, so d square x by dx, if you have to differentiate this, then 2 will come out, x will be there, then 2 minus 1 will become. Why minus 1? Because you just add a negative sign to what n is. In this case, our n was 2. Similarly, if we take very few basic examples of this more, then see, if you have an example, dx to the power 5 by 2 by dx. So see, 5 by 2 will come out. 5 by 2 will come out, and what will be left? X to the power 5 by 2 minus 1. You subtract minus 1. Now n in this case becomes 5 by 2. So see, this will be 5 by 2 will be there, x to the power. This will be 5 minus 2 by 2, that is 3 by 2. So this is 3 by 2. Or if you have such a case, dx where x has the power half. So see, half will come out. What is left now? If half comes out, then x to the power half minus 1. So this becomes now negative. See, 1 by 2 will be there. X to the power 1 minus 2 by 2 means minus 1 by 2. So this is minus 1 by 2. Then see, you have few properties of differentiation that you should know. If we talk about the properties of it, see, first is the constant function property. If you have a constant where, let's say, y is equal to k, now if you differentiate this y, dy over whatever is your wave function given to you, so differentiation of this constant, this will be 0. Like if you have 3, y is equal to 3, then if you differentiate d3 over dx, this will be 0. So if you have a constant, then your differentiation will come out to be 0. Now see, if you have the product of constant and a variable function, if you have, this is your constant and this is your fx, means variable function. So how do you solve if you have the product of constant and variable function? See, if this is the case, dy over dx. Now write whatever is the value of y. This becomes dfx by dx. Now see, k is a constant, so k will definitely come out. So here k will come out automatically, and dfx by dx will be left. Now see, how do you solve it if you are given a number? If you are given a number, how you solve it? Like example, if you have 2x square, let's say 2x square we are differentiating. So y is equal to what? 2x square. So you have d 2x square by dx. So this 2 will come out, this constant 2. First we have taken this constant 2. Now what are we left with? X to the power 2. So we know how to solve x to the power 2. 2 comes out, it becomes x to the power 2 minus 1. This is how we solve it. So see, this is what? 2 into 2 multiplied by 4, x to the power 2 minus 1. That is x to the power 1 only. So this becomes 4x. That's how you solve it. If you have such a function where constant is also given and you have the variable also. So first eliminate the constant, solve the variable the way you solve it, and once you get it, just multiply both of them the way you do it. One more thing, let's take one more example of it. If let's say sum is given to you as d, let's take a constant, the constant, let's take it as d3 by dx, or let's take this combination of constant as well as this. So if it is given to you as d3 over dx and your number is 3 by 2, 3 by x square. So here in this case, I have given you y as what? 3 by x square. So you have to differentiate 3 by x square now. Now see, if you have y is equal to 3 by x square, then you will write it in this manner, d3 by x square. So again, this is what? 3 is your constant, x square means 1 by x square is your variable now. So what's the method? Take out the constant. Constant has been taken. Now what is left? 1 by x to the power 2. So 1 by x to the power 2 is what? X to the power minus 2. So I can write it as 3. 3 has been taken common. Now what is left? Or in this also I can write it as 3x to the power minus 2. So if you are given your function in the denominator, just do one thing. Just reciprocate it. So whatever is the sign of your power, that will become the opposite. If it is minus, it will become plus, and if it is plus, it will become minus. Now see, 3 is common again. X to the power minus 2. Constant will come, x to the power minus 2 minus 1. X to the power minus 2 minus 1. Now see, 2 multiplied by 3 gives you 6 minus 6, x to the power minus 3. That's how you solve if you have a product, if you have to take the product of the variable as well as the constant. All right. So before moving on to addition and subtraction, just note down these.
Teacher, by the way, is this the start of the new chapter?
Yes, actually, Khalid, there's a lot of differentiation involved in this unit. So that's why I'm just discussing calculus once. We have discussed calculus meanwhile whenever we were discussing electric field. But in this chapter, this is specifically used. That's why we are just discussing it in brief. Then we'll start with electric potential only. Now, see, if you have addition and subtraction with you, we'll just discuss addition and subtraction. Now, see, if you have addition and subtraction, so whatever are the combinations given to you in between those plus minus signs, just solve it the way you solve it and at the end add them. Like if I give you an example, if you have the function as y is equal to x cube plus x square plus x, this is the function that you are given. Now see, whatever are the functions in between these plus signs, means x to the power 3, x to the power 2, x, solve it individually. If you have x to the power 3, 3 will be the constant that will come out. X subtract 1, 3 minus 1 becomes 2, 3x square. Plus 2 will come out. This will become 2. X to the power 2, then 2 minus 1 will be 1. So this will be 2x. Plus x to the power 0 is already there. So what will it be? See, 1 will come out. 1 is the constant. X to the power 1 minus 1. So x to the power 1 minus 1 is what? X to the power 0, which is equal to 1. So that's why whenever you have x only, we don't differentiate it. The reason is also that if you have x with you, if you differentiate, that becomes dx over dx. This also becomes 1. All right, so that's how you solve it. So this will be 3x square plus 2x, and differentiation of it gives 1. These are the basic properties of differentiation that will be involved. Now let us just quickly discuss integration also, so that if it is required, we are able to solve. Now see, in case of integration, if you have very small variables with you, already you have a very small part of it, let's say a very small part of the rod, and you wish to expand it. Whenever you are required to expand anything, you use this function integration. All right, now see, in a polynomial function, if you are given with x to the power n dx and you are asked to integrate it from x1 to x2, this is a polynomial generalized function. Now how do solve it? X to the power n, this becomes plus 1, and whatever is there in the power, just divide it, n plus 1. And whatever are the limits, write it from x1 to x2. Then the next step involves 1 by n plus 1 will be common, will come out. Why? Because it's a constant. X to the power n minus 1, instead of writing x all the time, write the upper limit minus the lower limit. Like if you have x2 as the upper limit, then it will be x2 to the power n plus 1 minus x1 to the power n plus 1. That's how we write it generally. So I think integration you all will be able to manage. I'm giving you a question, you try it yourself. Just first note down this. Till here, note it down: addition and subtraction. A question I'll give you. Yes, so these two are the examples. So all those who have written it down, just try those questions and send me your answer. This is very easy one. Once we have discussed, when we are on through to this both these examples, and we'll be discussing a potential. So just submit your answers quickly. This is both of these are very easy. Yes, answer of the first example, 4x cube dx, integration from 1 to 2. Hania, Khalid, Memuna, Samaira, Sara, all of you answer. This is the generalized formula. Memona, Samira, Saira, you also try, at least submit the answer of the first part, first example. So only Samira has given the correct answer. Okay. Now see, 4x to the power cube dx. See, 4 will come out. X to the power cube. 3 to add 1 to 3. So it becomes 3 plus 1, and whatever is in the power that gets divided means 3 plus 1. And then write the limits from 1 to 2. Now see, 4 is there, x to the power 3 plus 1 becomes what? It becomes 4 only. Divided by 3 plus 1 becomes 4. Powers are from 1 to 2. See, 4 will get eliminated, both of them will get cancelled. Now upper limit and the power to what is written. Upper limit is 2, 2 to the power 4, minus lower limit, and whatever is the same power 4. So 2 to the power 4, this is 16, minus 1 to the power 4 is 1 only. So this becomes your final answer, 15. All right. So did anybody get the answer for the second part? Let's discuss it then if nobody got the answer for the second part. Now see, again in this second part as well, 4 will come out. What are you left with? X to the power minus 2. And the integration is from minus 1 to plus 1. Now see, 4 will come out, x to the power minus 2, add 1. Whatever is there in the power, that gets in the denominator, minus 2 plus 1. All right. Now see, the limits are from minus 1 to plus 1. Now see, this is 4. Minus 2 plus 1, this is minus 1. So this becomes x to the power minus 1 divided by minus 1 only. And the limits will be the same. Limits will be from minus 1 to plus 1. So 4 divided by minus 1 is what? It's minus 4 only. So this is minus 4. Now x to the power minus 1 is the term that is left, x to the power minus 1, and the powers are from minus 1 to plus 1. These are the powers that you have. Now see, minus 4, your upper limit is 1. 1 to the power minus 1 minus lower limit, that is minus 1 to the power minus 1. See, upper limit and whatever is the power subtracted to the lower limit and whatever is the power. Now see, you can write it in this manner. No, 1 to the power minus 2 can be written as 1 by 1. Means if you have 4 to the power minus 2, if you take the reciprocal of it, 1 by 4, the power becomes positive. Similarly, if you have 1 to the power minus 1, you take the reciprocal of it. Here, instead of minus 1, this will be plus 1. So this will be 1 by 1 minus 1 by minus 1. So this becomes plus, this becomes 1. So now see, 1 plus 1 is 2, 2 into minus 4 becomes minus 8. Clear? So note down the solution, and once you are done, just text me. Then let's start the second chapter. Ani, the screen is not visible to you.
Now it is, ma'am.
It is visible?
Yes, ma'am.
All right. Done? Rest of you, are you done? Are you done? All right.
Yes.
So most of you have completed. Fine. Now let's begin with the chapter. Now, electric potential and capacitance. This is your chapter number 2 of NCERT. Electric potential and capacitance. All right, this is your chapter 2nd of NCERT. Now see, in this first we'll be discussing this term electric potential. We'll be discussing this term electric potential. So all of you, I think, should remember what is meant by work done. So work, energy, and power you have done in your 11th standard. So what is work done? Work done will, the whole concept of work done will be utilized in electric potential. Now see, work done, when we talk about work done, so at least you should know basic formulas of work done. Like work done is the dot product of force and displacement. So this is F means whenever you're taking the dot product, take the magnitude of the first one, take the magnitude of the second one, and add the cos theta. This is valid for when? This is valid for a constant force. If you have a constant force, this is valid. And if you have a variable force, just now we have studied integration. So whatever we have studied in integration, f dot dx, lower limit x to the power 1 to x to the power 2, means this is the displacement. This is valid for a variable force. So at least now you should be able to solve dot product and integration. And integration we have just revised it. So this is for variable force. Now see, regarding the concept of electric potential, what is meant by electric potential is this. Suppose I have a charge plus Q. So similar to electric field, this charge is having its certain potential. So we call this plus Q as the source charge. The way we had source charge and test charge in case of electric field, similarly, we are considering this source charge right now. Now see, I take up this charge is there. This is the source charge, so this is stationary. Now I bring another charge. This is Q, small q charge. This is my test charge now. All right, so again, the similar concept of source charge and the concept of test charge. Now see, test charge is small q. So now see, if I bring this small q at a point, all right, this, let's say this point is some point A. And here this q charge was at infinity. Somewhere very far away beyond our reach, this was at infinity. Now from infinity, I have brought this test charge to some point A. Let this point be A. So in order to do this, means to bring the test charge from infinity to a point, some work done will be required, because without work done, I won't be able to bring up a stationary charge to another point. So this work done to move a charge from infinity to a particular point, this is known as electric potential. Now the condition that occurs is that it occurs against the electric field. See, it will also be having its own electric field. Now you are not bringing this charge because of this source charge. This source charge is there. This is stationary. But what are you concerned with? You are just concerned with the test charge now. You are bringing the test charge from a point at infinity to a particular point, which is done in the opposite direction of electric field. And also you should remember one thing, that no acceleration is produced in this case. Whenever you are bringing out this movement, no acceleration is brought. So similarly, the way we had an electric field, in electric field, what happened? Electric field was the property of a single charge. A single charge was present whose environment had certain electrical properties in which we could experience electrical phenomena. So we called that space as electric field. But electric field was a vector quantity. So that same thing, if I drop it into a scalar form, then I call it as an electric potential. So electric potential will define the electric properties around the charge in scalar form. Whereas in case of electric field, all the properties were defined in terms of vector form. There you had to consider the direction. When you were implying or doing the application of superposition principle, there you took all the directions of different electric fields. Then by considering in mind all the directions of electric field, you used parallelogram law or whatever law possible, and then finally got the net electric field. Electric potential is similar to electric field. It's just that it is the scalar analog of electric field. So here you are not concerned with the direction. So one part of direction gets removed because this is a scalar quantity. So what is electric potential? It's the work done to move a charge from where? From infinity to a particular point. So how it is a work done? Let's see. Let's relate it with the work done. Let's relate electric potential with work. Firstly, you have to remember that electric potential, it defines the electrical properties. It defines the electrical properties around a charge, in scalar form. All right. So it defines the electrical properties around the charge in scalar form. And again, similar to electric field, this is the similarity with electric field, and opposite to the electric forces, that this is the property of a single charge. The way in case of electric field, one charge was sufficient to produce its own electric field. Similarly, in case of potential, one single charge is enough. So it's a property of a single charge. So potential is what? The way I had taken that point A, if at particular point A, I am bringing up a charge from infinity, then my change in potential means VA, final point, minus initial point, means potential at infinity. This is equal to what? This is equal to the work done in bringing it from infinity to that point per unit charge. So if you have a unit positive test charge, if I put this as 1, if Q is equal to plus 1 coulombs, then my potential will be equal to the work done. So that's why we say electric potential is what? Electric potential is the work done in bringing the charge from infinity to a particular point. Now say potential at infinity is 0. So you can simplify and write VA directly as work done to bring the charge from infinity to that point divided by the charge. No need to write potential V divided by VA minus V infinity all the time, because potential at infinity is 0. So if you have to define electric potential, it is the work done. It is the work done in carrying. Now, what kind of charge? Unit positive test charge. Carrying unit positive test charge from where? From infinity to a particular point. To a point, you have to remember that against, this is done against electric field. And also you should keep in mind that no acceleration is produced. So, and without acceleration. Without acceleration. So yes, Hania, tell me, is it a scalar quantity electric potential or a vector quantity? Yes, Hania?
Scalar.
Scalar. It's a scalar quantity. So all the properties of scalar quantity will be applied. So you don't need to consider the direction. You are not concerned with the direction now, the way you are concerned with the direction in case of electric forces and electric field. All right. Now you are not concerned with the direction. Salman, tell me the SI unit of potential. This is the formula. What will be the SI unit? This is the formula. Potential is work done per unit charge.
J by C, sorry.
Yes, correct.
Joule.
Joules per coulomb. Perfect. J by C, that is joules per coulomb. One more thing that you have to remember, 1 joules per coulomb is also called as volt. So you have the SI unit of potential as joules per coulomb also, or as volt also. All right. So the concept of electric potential is clear.
Yes, teacher.
Yes, ma'am.
Just note down these things, then we'll derive out the formula for it.
Teacher, can you scroll down?
All right, so I think all of you have written it by now. So if anybody is writing, just let me know. I'll wait. Otherwise, let's do the derivation of electric potential for a point charge. So we have calculated an electric field for a point charge. Now we have to find out what is electric potential for a point charge. Now I say I have this point, I have this charge plus Q. All right, this is my source charge. Now see, this is some point A. At infinity, I have this charge, small q. This is the test charge that I have. All right, now in between, I take a very small portion of it. From infinity to A, this charge is being brought up. Let's say this point is C, this point is D. So let's name few things, like let's say this is small r. From the charge that we have to the point, let's take the separation of capital Q and small q as x. And the very small portion that I have driven in between, this is dx. All right. Now see, both of them are positive. Plus small q is positive and plus capital Q is positive. Now see, Memuna, you tell me, due to plus q means capital Q, where will the force be applied on small q? Towards the right or towards the left? Right. Towards the right hand side, because both of them are positive. So this will push it away. This will be F. Now see the external force that will also be applied on this charge, because both are positive, so both will apply on each other. So this will be the direction of F external, because that will also be pushed. Now see, F external, what will F external will try to do? F external will try to push Q back, because the force of repulsion is occurring from plus Q. So that's why the external, what is the function of external force? External or force always tries to bring the object or whatever you have back to the original position, and it acts against the force. So since your force is acting towards the right hand side, your external force acts on the left hand side, so as to bring it up in neutral position or to move it. Now see, on application of Coulomb's law, if I have, so yes, Sarah, you tell me, these are the two charges you have, small q and capital Q. If you apply Coulomb's law, what will be the force? Capital Q and small q are the charges. If you apply Coulomb's law, yes, Sarah? Sarah, you have missed one thing. Is this only the electric force that we use? One of the major things, yes, correct. Constant you were forgetting. K, capital Q, small q. Now tell me, should I actually use R square? Sarah, you tell me. R square is the separation between this capital Q and point A. So should R square be written?
X square.
X square. Because X is the separation. So on application of Coulomb's law, this becomes K, capital Q, small q divided by X square. And F external, this is negative of force, because both are acting in opposite direction. So your F external, or let's say your F external only, this is K Q by X square. This is. Now see, work done carrying the charge from smaller points that we have taken. These smaller points from C to D. Just we are talking about this small point, C to D. All right. So separation from C to D, we have taken it as dx. Now see the work done. Work done will be what? Work done is F external dot dx. The way we have discussed how to solve work done, these are taken as the dot product of force and displacement. Now see, from C to D, I am moving in this direction. C to D, I am moving. And my force, this is acting in right hand side. So both of them are in opposite direction. That's why the force angle between the force is taken as 180 degree. All right. So cos theta, because you have to consider. So work done will be what? Work done will be F external dx and cos 180 degree. Cos 180 degree is -1. So I'm writing this minus sign in advance already. So the reason for this minus sign is this only, because angle between displacement and external force, this is opposite. So that's why angle is taken as 180 degrees. Now see, dw because we have taken a very small element. So we do not get the whole work done, we get a very small element of the work done. dW is equal to minus F external dx. Now F external we know, dW, this will be minus K capital Q small q x square dx. Now see, we have to integrate it. Now from where to where? But electric potential was what? It was the work done to carry the charge from infinity particular point, and that point is at the separation from Q till what? From capital Q, this point is located at a separation R. So from infinity, we are bringing the charge to a point at a separation of small r. So from infinity to R means to point A basically. This is the definition of electric potential. Now see, we have just practiced derivation, integration, how to solve it. So your whole work done. K capital Q small q, this is a these are constant. You are left with x to the power minus 2 dx, and this is from where? Infinity to the point R. Now see, capital K, this constant, capital Q, small q. All right. This is what? X to the power minus 2. Now see, x to the power minus 2. You add minus 1 over here, and whatever is there in the denominator, that is written. So this is written in which manner? This is written as x to the power minus 2 only, no? This is x to the power 2. Okay, now we have a negative sign as well. We have this negative sign as well. Wait. We have one more negative sign as well, this negative sign. So that has to be considered as well. That negative sign which we are taking. This is because of cos 180 degree. Force and displacement are separated from 180 degrees. Now see, if you just not write this, just don't write this part, because we have to keep in mind negative sign also. So till here it is clear. Now see, work done will be what? Negative, or along with this, now bring it up. K capital Q small q. Now this is the constant that you can bring up, and what is left? Dx by x square from infinity to the point R. Now minus capital K Q small q. This is, now see, what will be left? 1 by x will be left, because x to the power minus 1 will be there. And you can remember it directly whenever you have integration of 1 by x square. Remember, that is given by minus 1 by x. So if you remember it, you can directly put it. So this is from infinity to the point R. Now see, again, whenever you have upper limit and lower limit case, whenever you have such a case, take minus q, k, capital Q small q, upper limit, put it first, means 1 by R, put it first. So this becomes 1 minus 1 by R. And if you multiply it with it, don't take the minus sign common. You can multiply it directly, so that you'll get the answer in one step only. Now see what we have done, minus kq to the multiplied by minus 1 by x from infinity to small r. Now just take it as minus 1 by r. So this will become minus multiplied by minus. This will become positive 1 by r. And minus infinity will be left, minus 1 by infinity will be left. So see what does it become? K capital Q small q divided by r. Because 1 by infinity is 0. Now as I've told you, the definition of potential is only work done per unit charge, the test charge. So if you want to calculate for potential, this will be K capital Q small q by R along with this small q. So your small q gets eliminated, and potential is K Q by R. Now see, you can compare it with force, compare it with electric field, or you can write it in this manner also, 4 pi epsilon naught small r. This is the formula for potential due to point charge. Now remember, electric field was what? Force was what? Force was K Q square by R square. Both were squared. In case of electric field, you had k q by r square. In case of potential, you have k q by r. So remember all these three formulas. This is for force, this is for electric field, and this is for potential. Clear? Yes, Khalid, Sarah.
Here.
Yes, ma'am.
All right, just note it down.
Ma'am, V is equal to KQ by R is for?
V is equal to kq by r is for the potential.
Okay.
Okay, force, F is force, E is electric field, V is potential. So this is a method to remember all the three formulas.
Okay, ma'am.
All right, all those who have to pray, you can leave and come back in 5 minutes till the time rest of them are noting. Done? So are you all back now?
Yes, ma'am.
Oh. Oh. Now see, electric potential is a scalar quantity. So see, whenever we did electric force, what did we do? We took out the magnitude of the charges. In case of potential, if you have a charge plus q at some distance from r, at this point you have to calculate the potential. So this becomes q by 4 pi epsilon naught small r. If you have minus q and you have to calculate at this point small r, so see, this will be now not you have to just take the magnitude. Since it's a scalar quantity, you are not concerned with the direction. Take it as minus q 4 pi epsilon naught smaller. See, in case of forces and in case of electric fields, what happened? You took the direction. So that's why you were not concerned with whatever is the magnitude, be it negative or positive. Now, in case of voltage or potential, you just have it. You don't have any other direction because it's a scalar quantity. That's why you have to consider it. Now, see, let's do a very basic example, formula-based equation. So if this is a charge minus 3 millicoulombs, I have to calculate potential at this point. Let's say this point, and the separation from this point is 9 millimeter. Let's say this point is some point A. And you have to calculate the potential. So now see, V is equal to what? V is equal to K Q divided by R. This is the formula for potential. So see, V is equal to, what is the value of K that I should put? What is K? Yes, constant K, what is the value? You have done this in Coulomb's law also, in case of electric field also, this K was constantly used. Yes, Hania, Memuna, Samaira, Sara. What is the value of the constant? Yes, Hania.
9 into 10 raised to 9.
9 into 10 to the power 9. There's nothing to think so much. The value of constant, this is 9 into 10 to the power 9. All right. So, yes, Memuna, what is the charge that I should take? Yes, how much? Only 3?
Minus 3?
Only minus 3? Just look at the SI unit.
Yeah, minus 3 into the power of minus 6.
Millicoulomb, not microcoulomb.
Minus 3, I guess. 10 to the power of
Minus 3.
3.
Minus 3. This is minus 3 into 10 to the power minus 3. Minus 3 millicoulombs divided by. Yes, Samira, what is R that I should take? What is the value of small r that I should take? This separation.
9 into 10 raised to minus 6.
Again, not 6C. Why you all are forgetting? When you have 1 micrometer is equal to 10 to the power minus 6 meter. If you have 1 millimeter, that is 10 to the power minus 3 meter. So this will be 9 into 10 to the power minus 3 meters only. All right. So 9 will get cancelled. Potential will be 10 to the power minus 3, 10 to the power minus 3 will also get cancelled. Potential will be minus 3 into 10 to the power 9 volt. All right, formula. This is how you use the formula of potential. Just note down this as well. Done? All right, so all of you are done. So electric potential for a system of n interacting point charges. Now see, if I have a charge Q1, I want to calculate potential at point P due to this charge Q1. And let's say the separation of Q1 and this point P is R1. I have charge Q2 also, and I have to calculate potential at this point P only. But the separation of Q2 and Q2 and point P is R2. Similarly, I don't know how many charges are present, but let's say n number of charges are present. So if Qn is the number of n number of charges present, and let's say the separation of this charge from this point, this is Rn. So you have you have n number of charges with you with n number of separation of them from the point charge. So see, V1 will be what? V1 will be given by Q1, KQ1 by R1. V2 will be given by KQ2 by R2. Vn will be given by KQn by Rn. This is the individual potential. These are all the individual potentials due to single charges. But still, I'm not able to get the net potential. So, net potential will be V1 plus V2 plus V3 up till Vn. Just the difference that comes in case of superposition principle for electric field and force was that you had to take out the direction first. When you took the directions, then you put the magnitude. Now in this case, you are not concerned with the direction. So simply whatever you are getting, if -2 is the potential you are getting, then subtract. If you are getting +2, then add according to the sign, because you have to keep the sign in mind. So for a system of n interacting point charges, electric potential at a point. Now see, when we did superposition principle, we wrote the same statement. It's just that it came electric field at a point is the vector sum of individual charges. Here electric potential at a point is algebraic sum. This is the algebraic sum of potential due to individual charges. So we'll do questions on it today. We'll do questions right now only. But before moving on to the numericals, note down one thing as well. In this question, in the numericals that we'll be doing right now, this concept will be used. See, at point A, if you have charge Q and potential will be VA. At point B, you are moving this charge. So potential is VB. So as I've told you, work done will be what? The difference of the potential. So work done in moving the charge from A to this point B. Work done from moving the charge from A to B will be given by Q multiplied by whatever is the potential difference. Means VB minus VA. So work done by the external force to carry the charge small q. How? Because VB minus VA was what? This was work done by AV by Q. This we had seen. So if you are asked to get the work done, just multiply this term with Q. So you get the work done. Also remember one thing. If you are asked to calculate work done by electric field, then remember work done by electric field, this will be negative. So whatever is the work done external, both are negative to each other by the electric. So if you are given the work done by electric field, don't forget to take this negative sign. So if minus is given, minus minus will become plus. If plus is given, then it will become minus. The sign will change because this is the relation. All right. So note down this and we'll do some questions. Some numerical practicing we'll do. So you have to calculate the work done by external force in carrying electron from this point to this point. So voltage at A is 10 volt, VB, that is voltage at B is given as minus 20. Charge you should know on an electron. Take the difference between them, multiply it with the electronic charge, you will get the work done. Take 2 minutes and at least try this question, formula based question, based on this only. See, work done by external force in carrying electron from A to B. Potential VA is given to you as 10 volt. Potential at B is given to you as minus 20 volt. So work done by carrying the electron from A to B means final potential minus initial potential will give you the potential difference. So final potential will be VB minus initial potential. Initial potential is VA. This is equal to what? Charge means the charge of an electron multiplied by the work done. Now VB you know, VA you know, Q you know, you have to calculate work done. So see, VB is minus 20, VA is 10. So this becomes minus 10 is equal to, what is the value of Q that I should take, Khalid?
Ten.
Q. What is your charge over here?
1.6.
Correct. 1.6 into 10 to the power minus 19. See, charge you are taking, but charge on what? Charge on the particle to which you are moving. And the particle over here is the electron. So charge on an electron, you know, it is 1.6 into 10 to the power minus 19. But as I've told you, in case of potential, you have to take the sign as well. An electron is a negative particle, negative entity. So you add minus 1.6 into 10 to the power minus 19 multiplied by work done by the external agent. So see, work, not charge won't come over here. Charge will be with potential. Charge will get multiplied with potential. See, work done by charge is equal to the potential. So work done will be potential multiplied by the charge. So Q will come in this side, not with work done. This is work done by external. So this is the electronic charge and work done by external. So work done by external will be what? The electronic charge is minus 1.6 into 10 to the power minus 19 multiplied by minus 2 minus 10 is what? Minus 30. So 3 into 1.6 will be 4.8. So this will minus will become plus. So this will become plus 4.8 into 10 to the power 1. 10 will get eliminated, minus 18 joule. So if you multiply both of them, because of the 0, 1, 10 will get eliminated, and 1.6 into 3 is 4.8. Minus into minus is plus. So this is how you solve it. Just note it down. I'll give you one more question similar to this one. So this you should be able to submit. This is a question similar to what we have done just now. Everyone should answer right now. All of you. Quickly answer. The calculations are not even tough. Memona, you are not submitting work done by electric field. We have discussed if you are given work done by electric field, then how do you calculate? You have given the answer for work done by the electric force. Yes, Samaira, correct. Samaira is right. Rest of you also answer. The calculations are not lengthy of this part. Hania, you submit. Sara, rest of you. Salman, Khalid. See, Sara and Khalid. Now the charge is not electron. Electronic charge is not there. Charge is given to you as 2 coulombs now. Charge is already given to you as 2 coulombs. Salman, you also try. Submit your answer. See, so till now the correct answer is given by Samaira only. Look, you have to calculate work done by electric field. Firstly, remember, you have to calculate work done by electric field. So read the question carefully. In carrying charge 2 coulombs from point A to point B. All right. Now see, final potential is VB, initial potential is VA. This is the change in potential multiplied by the charge gives the work done by the external force. All right, this gives the work done by external force. Now VB is given to you as 15 minus VA is given to you as 5. Charge is given to you as 2. This is work done by the external force. 15 minus 5, this is 10. So this becomes 10 into 2. This is work done by external. So work done by external force becomes 20 joule. Now, do we need to calculate work done by external force? We have to find out work done by external field. So work done by external force is equal to negative of work done by electric field. So work done by electric field is equal to minus 20 joules. How you were getting answers in the powers of 10, Sarah, Khalid? 10 to the power minus 18. Yes, it will be
I
minus
accidentally
22.
took the minus
Charge
19
as,
also.
what did you take?
I took 10 to the power minus 19 also. That's why I got the wrong answer.
Okay. Okay. So is this clear now?
Yes, teacher.
Just note it down. Then we'll do one last numerical. Okay, Salman. So if you're getting 20 joule, that is work done by electric force. So you have to add a negative sign, that will be work done by electric field. So whatever question comes by electric force or electric field, just read the question and answer accordingly. If it is electric force, then till here your answer is correct. And if it's work done by electric field, then you have to bring it till here. See, this is the figure that you have. It's a regular square with A, B, C, D, these 4 points. At the vertices, you have plus E, minus E, plus 2E, minus 2E kept. And the side of the square is A. Both the diagonals of the square intersect at the central point, which is O. You have one additional point E at the middle of CB, means dividing it into A by 2, A by 2. Firstly, you have to find out the potential at point O. See, for finding out the potential at point O, now we don't need to consider the direction. So simply we'll be writing for the first part. First, we'll write what is VA. VA means at point O, what is the potential? See, now potential's general formula is KQ by R. K is the constant, Q for A point is E, R is this separation AO. Then VB. VB is this point, means minus KE divided by BO, this point. For point C, VC, this is plus 2E. So K, now the charge is 2E, separation CO. Then potential at point O because of D minus K2E by D. These are the four potentials. Now see AO, BO, CO. Let's see what are these equal to. See AC, this diagonal. If you look at this triangle, this is point B, this is A, this is the diagonal C. You know this is A, you know this is A. So you can easily find out this hypotenuse using Pythagoras theorem. So AC will be what? AC will be root 2 by 2. Why? Under root of A square plus A square, this gives root 2A square, root 2A square. This becomes root 2A. So root 2A when you divide it by 2, not AO. This becomes A root 2 by 2. Or you can write it as A by root 2 only. So AO which is equal to BO which is equal to CO which is equal to DO. This is equal to A by root 2. Is this clear to all of you how we have got A by root 2?
Yes.
Okay. So A by root 2. Now if you put it, if you take out the net potential, this will be KE by, now see AO, BO, CO, DO all are equal to A by root 2 minus KE A by root 2 plus K2E by A by root 2 minus K2E by A by root 2. See, this is getting cancelled, this is getting cancelled. Net potential at the center VO, this is coming out to be 0. First part is clear to all of you?
Yes.
Rest of you?
Yes,
Yes,
ma'am.
ma'am.
Here.
Now see, what does the second part ask? See, at this point E, you have to calculate the potential. Now see, for calculation of potential, you just require the separation of the charge from that point. So at this point, you know the separation of E, this is A by 2. 2E, this is A by 2. But do you know the separation of point A plus E and point D is minus 2E? This you are not aware of. But see, we will be able to calculate DE and AE. If you look at this triangle carefully, this triangle, then see for the second part, this was the triangle, no? This was B, this was A, and that was E point. EB was given as A by 2. AB was the side of square as A. Again, you can apply Pythagoras theorem. So see, if you apply now Pythagoras theorem, AE will be equal to what? AE will be equal to A square plus A by 2 whole square, which becomes A square by 4 under root of it. This is AE using Pythagoras theorem. Simple Pythagoras theorem. So 4 multiplied by A square, this is 4A square plus A square. If you take the LCM, divided by 4 under root, this is AE. So this becomes 5A square by 4 under root. So A square by 4 can come out. It's A by 2 under root 5. This becomes A root 5 by 2. So you have the value of AE now. If you know value of AE, you will be able to know the value of DE. So AE, which is equal to DE, is equal to root 5A by 2. Now see, if you have all the separation of the charges from the particular point, you can easily get the potential. See, this is the figure that you have. Now see, potential at E due to this A. All of you write me in the chat box, what will be the potential at E point because of A point? You know the separation now. You know the charge, you know the separation, put the constant. All of you write me in the chat box quickly. You know the separation now, AE. You know the charge. Yes, nobody has answered till now. See, potential is what? K Q by R. K is the constant that will remain same. What is the charge at point A? What is the charge at point A?
Plus E.
Plus 1.
Plus E. So KE. And what is the separation? We have just now calculated the value of AE. So why you were not able to answer? See, potential at A, at point E because of A. K is the constant. E is the charge that is given. And the separation is what? Root 5A by 2. This is VA. And if you take VB, now see, VB is what? What changes will come? Instead of charge plus E, you have minus E. And the separation of B point to E point. This is how much? This is A by 2. So in this formula, V is equal to KQ by R. K we know, Q is minus E, R is A by 2. So potential at B becomes minus KE by A by 2. This is VB. Then VC. See in VC, KQ by R. K we know, Q is what? Plus 2E. R again, separation of C and E, this much. This is A by 2. So potential at point C becomes what? This becomes K to E by A by 2. Then potential at D point. Now see, charge is what? Minus 2E, separation of point D to point E. This is what we have calculated, root 5A by 2. So this will be KE, this will be K minus 2E because negative 2 is there. This is minus 2E, no? This is minus 2E divided by A root 2 5 by 2. So minus K2E by root 2 5A by 2. These are all the potentials that you have. So the net potential at E will be what? V net at E. KE, just take the sum of all of them. 2KE by root 5A minus KE minus 2KE by A, then plus 4KE by 2 by A, then this part minus 4KE by, this becomes root 5A. So you can take KE by common at least from all of it. KE by A, KE by A, KE by A, KE by. Or you can even take this 2 common. You can take this 2 common. 2KE by A can be taken as common. So here it will be left 1. Here you have 1 by root 5. This will be minus 1 by root 5. Here you will have only 2 because 2KE by A has been taken common. And from here you will have 2 by root 5. All right. So this will be K 2KE by A, 1 minus 1 by root 5. This will be your final answer. Now tell me, each one of you, is this clear?
Yes.
Yes, ma'am.
What about the rest? Memuna, Salman, Samaira, Sara.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Fine. So this is how you calculate. Now see, if you are having any point, just take the separation of the charge to that point. First calculate the separation, then just put it in this formula, k q by r. K, you know, 9 into 10 to the power 9. Q, whatever charge is there, and R will be the separation. So if it is given E or it is given any other point, like it was given O. Now see, work done in carrying the charge from O to E. So see, for the third part, work done in carrying the charge from O to E will be what? Charge multiplied by final potential is what? O to E. So E becomes your final potential minus O, your initial potential, VO. This is how you calculate. So work done by OE, this will be, is the charge provided to you. Charge is not given to you. Electronic charge is given. No, E is given. Work done in carrying proton. Okay. You have to calculate work done in carrying proton. So proton has the same 1.6 into 10 to the power minus 19 charge. But since proton is positive, don't add negative sign. It will be protonic charge, that is electronic charge. VE, you know, 2ke by A 1 minus 1 by root 5 minus VO. VO we calculated at the center, it came out to be 0. This will be the work done. So final answer for work done will be just multiplied. This term will be 0, 2k E square, because E got multiplied by E, A 1 by 1 minus root 5. This is how you will do the calculation for work done. First, take out whatever is the final potential, subtract it from the initial potential, multiply it with the charge, that gives you your work done. All right, so just note it down, and wherever you get stuck, just ask me. Done?
Yes, ma'am.